So hello everyone and welcome to the second session of Topological and Metabolic Approaches to Ontogenesis with instructor Sha Xin Wei. As we did before the recording, I'm going to go over a couple of logistic things with you. There's two main important things that I want to ensure that you cover ideally like before or right after the end of the session. The first one is if you haven't enrolled in for presenting a particular text with a particular group, make sure you do that until the end of the class, just to make sure that we can actually accommodate you and yeah, that we can all see a little bit of your opinion about some of the texts that we are discussing. We're looking forward to seeing this. I'm going to send here the spreadsheet that is titled the presentation sign up. We have quite a few people who have already signed up for presentations, but if you didn't yet, perhaps if you joined the seminar later or if you didn't have the chance to, this is the presentation sign up sheet. I'm going to send all these links that I'm talking about on the chat. So presentation sign up sheet is there. The other thing is for those of you who have already spoke about and selected presentations, right? So for example, session 2, we have Emmanuel Kocha, The Life of Plants, and Introduction to Plant Biology. And for those of you who have already selected, we expect you to upload your presentations here and also your final projects there. Xin Wei is going to do more details about the final projects in when he mentions it. So this is the folder to upload presentations. To make sure that everybody can watch your presentation, discuss your presentation, and that these things get sorted out quite efficiently, we want to ask you to always upload your presentation on the Thursday before the session. I know that there wasn't, this folder was created, but it wasn't updated. I think it wasn't updated before, but you want now people who are doing presentations on the text from this week and also from the session 3 on individuation, you want to upload the presentations to this folder. If you have any particular like demands, like you have something and you're not able to make it, you need like a slide to edge on asking for a slide extension, do email student services and copy Raviv as well, who is the standing moderator for the seminar, and then we are going to figure it out, your situation and your group situation individually, right? Like case by case, we're going to analyze and help you to the best of our capacities. And so yeah, this is about, make sure if you didn't sign up for presentations yet, do it. It's the first link that I sent. If you have your presentation and you didn't know where to upload or anything, do it, please. People who are presenting this week, so for session 2, and people who will be presenting the text from session 3, upload them by Thursday, and then by Thursday you're going to be able to go there and also watch the videos and discuss them. If you want to drop a note about them on Discord, email any of the colleagues, and yeah, just to make sure that we have an interactive experience with that. And I pass it along to Xin Wei now. Xin Wei is going to talk a little bit about the final works as well, and more information about the course. Xin Wei, take it away.
All right, so I added some more details to the syllabus, which I also posted to the Google Classroom, with more specific pages of the readings that I expect people to look at. The supplementary, I do not expect you to look at. Supplementary would be like references to whole books that would act as a background, okay? And you're more than welcome to dip into them as much as you want, but it's the more specific page references are here, okay, for each week in particular. The other thing is this: there are more groups than topics, right? More groups than readings, right? So what I'm thinking about is that when you make your presentation or write up your reports for each of the themes, for the themes you sign up for, as I think it would be really good for you to also relate the readings that you do read to your own work and interests. That way, for sure, it will give us multiple viewpoints on the same material. And then, of course, to demonstrate that you have gotten something out of the material too. So that's what I'll be looking for. In terms of the final project, I'm thinking of short papers. I'm not sure what the conventions are for the new center. This is my first seminar, but I would be expecting short papers, meaning I'd say 10 pages or less, enough to make a point, and elaborate it, et cetera, et cetera. I'll give you more details then. Again, that would be something where you draw from the themes of the course and apply it to some of your own research interests, okay? Any questions for that? Good. So we have a lot to go through today because I wanted to introduce some basic concepts in topology and also then have a break and then switch to metabolism. Okay, some ideas from recent work in theoretical biology. So we'll see. Also, I'm not going to introduce all the mathematics that I think are useful in this one session. So we'll have chance to revisit them later on during the term. Okay, so but just to put it on the table, some comments about kind of methods, like how using this kind of stuff. Remember last time I was saying that I like to think about using mathematics as in the mode of propositionality. Like what if, right? What if we had these concepts at hand? What did Deleuze, for example, Deleuze did? He took some concepts like the notion of a manifold, and he called it multiplicity, etc. So what did he do with this? In order to think philosophically, right? So we can do the same. In this case, we can think about this kind of propositional use of mathematics rather than instrumental use of mathematics, right? Instead of using math to describe something, that's what the scientific use would be. Another point is this idea of why topology? Because mathematicians, well, if you go ask mathematicians, say, well, this is what people learn in the very beginning of their studies in mathematics. It's elementary. It's called elementary. But what I like to try to propose is that we use, in fact, the most elementary concepts in mathematics and build up concepts as appropriate to the phenomena that we want to try to understand, rather than take a very fancy body of mathematics and then like a hammer thought, right? And then start to look everywhere for the nails. Everything turns into a nail, right? You have a very beautiful, elaborate machinery, and then try to then impose it polymorphically, in fact, on everything. So no, we want to try to build things up. And then topology is the simplest set of structures, mathematical structures, that lies above bare set theory. And we can say more as we go, okay? It gives us some grip on phenomena, and yet doesn't have so much structure that the structure itself would tend to over-determine the kind of insights we might get out of deploying these concepts, okay? Second point. Third point is to be careful also to avoid what the Nurembergs called the Pythagorean snare, the Pythagorean error, which is I will be describing concepts using drawings on pieces of paper and using some concrete examples, right? Hopefully as a way to get into the concept, but let's also try to remember that that the concepts will exceed the representation of the concept. Okay, so we don't want to mistake the drawing for the concept, right? Actually, I saw a talk by Cecile on Simondon, and I think she made a similar point actually about this. So having said that, let's start with some examples. Remember last time we talked about some examples, Earth, where does the Earth stop and where does the space begin? And smoke. The thing about smoke is if you ask where's the smoke, right? That's actually quite interesting because it's not just a matter of physics, it's also who's smelling, right? So and also who expects it. So it's a physical, physiological, and phenomenological question, right? All at once. So it's a quite nice thing to say, ask where is the smoke? Another example was songs, the set of all songs. And here I want to bind in right from the get-go performativity, right? Not songs as written in a book, right? But the singing of songs and all the singings of songs that had ever been sung and will be sung, right? So there's an indeterminacy to that family. So it's not really a set. It's more indeterminate than that, okay? So just think about all these kinds of, and I asked you, I remember last week, to think about your own examples, and maybe you can mention them in your own presentations. So as basically sufficiently concrete families, assemblages for us to try to topologize, okay, as we go. Notice one thing I did not say is graph, the figure of thought, the model for so much of cognitive science and for computer technology today. So that's why I want to introduce topology. It's actually a lot richer than than the classic model of a graph, right? Which underlies so much of contemporary thinking when we try to think about computer technology or about taxonomies of anything, right? This kind of graph structure. Whether it's models of the mind or models of economics or models of computation, models of thought, et cetera, et cetera. So I want to put these aside because one of my claims is that these kind of structures, they're actually quite a tiny fraction of all the kinds of mathematical structures that are available to us to think with. And unfortunately, they have so overdetermined the kind of theories that people come up with in these different domains that I would like to try to break through that logjam, okay, with topology. Okay, so concepts. So if you start with something, I'm going to draw pictures on the paper, all right? So if you have some, let's say here's a space with funny shapes in them, some dots, some lines, some squiggles. Here's a bunch of stuff, okay? And imagine that some of these might be just dust you sprinkle, or some might be blotches, and some might be moving around even, okay? And we want to try to understand and think about this in the cases of like songs or whatever. And remember, again, I'm drawing pictures. So I have to be very careful because, for example, the space of all sounds is not something we can draw. Okay, but suppose we just start with something that we can draw, like this kind of mess of shapes and dots and squiggles, and we want to find a way to think about how to describe it, or I'm sorry, how to capture it, how to make some understanding of the kind of the sets that would be most adequate to this, right? So we can think about one way to do it is to, for example, since we're in a plane, okay, we can cover them with disks of various diameters, okay? So can you see the green? Can you all see the green circles? All right, good.
Yes,
so,
yes.
Thank you. So now I'm covering, which is a very messy, complicated structure. I don't have words or equations or any kind of way to describe it precisely, right? But at least if I can cover it, I can cover it though with something simple, that is a disk, these kind of circular regions, these plates, right? So this is a basic starting point for topology, okay? Now that you want to describe arbitrarily complicated sets, with some sets, in this case, the green sets that are more amenable. Now, the beauty of topology was that we wanted to find, mathematicians found a way to describe the green, right? Kind of the amenable, was a covering, whole space, it's called X, okay? And look at the fundamental qualities of covering that we would like to retain, okay? What was some of the fundamental properties? Well, we'd like to say something like this. If you have two of these amenable sets, this one and here's another one, okay? Not both circles, let's say. But we like to say, well, you know what? The intersection should also be such a amenable set, okay? It's a natural thing to want, okay? Plus, if two of these are amenable sets, okay, then maybe any union of them is also a member of this family of amenable sets, because intersection and union are the most basic things you can do. In fact, this is the axiomatization of a topology. And I'll write this down more formally now, okay? So for topology, okay, it's basically a big set X, whatever it can be. It can be any kind of set, right? Plus a family of subsets, call that F, okay? May not be all the subsets, okay? That'll be maybe extravagant, but a subset, some subsets, okay? With the following property. Any two, if these are in the family, any two members of the family, remember this family is a family of subsets, okay? So the first axiom is any two, if you have two members of this family that are called, then their intersection is also in this family. That's what I drew here. Second, if you have two members of this family, then their union is also in this family, which is what I drew here. Put together, there's also a member of this family. So this way you can quickly create a way to cover anything, right? Oh, there's more. I just said anything, right? Which means we need to do two more things. We need to be able to say that this whole family covers X. If you throw them all together, they cover entire space. Nothing's left out. And one more, it also contains the empty set. It's just like those anal things that mathematicians have to think about, you know. Why? Because you might have intersections. You can see it, right? Because here's maybe one thing, one member of the family, a green, is another member of the family. They don't intersect. But I just told you, we want U and V. If you take intersection of U plus V is also a member of the family, intersection of these two is null set, is empty set. So to be consistent, for these axioms to be consistent, we have to allow that the empty set is in this family. Okay, don't mind me. The really important, interesting thing is the first two, unions and intersections are members of the family. Now, notice in the previous picture, I started with some particularly simple and amenable sets, disks. But you see, if I take two disks and I make the can you see this if I'm drawing green? I'm sorry, it's a very faint. Okay. If I take two disks and intersect them, I don't get a disk anymore, right? The intersection of two disks is just a loom, this kind of crescent shape. Therefore, this just a family of disks alone cannot be a topology. Cannot. You can start with a set of disks and you start generating using these axioms, all these intersections, all these unions, and see what you get. So that means this family of this topology, this particular topology that's kind of generated by disks is a lot richer. Its elements are not just disks. Its elements are much more interesting than that. Okay? 1 point. So that means we're no longer restricted to some things that are like a Platonic set of basic elements anymore. This allows arbitrary, well, in this case, arbitrary unions and countable intersections. That's a technical term. Okay. So now we have a way to think about how to chunk up this space. Notice, I've never used the word number here. I have not said anything about how far 2 points are from each other. There's no metric. This is the key thing. A metric would be something where for any 2 points, P and Q, a metric is a function on points PQ, which gives you a number called the distance between P and Q. So metric is for P and Q, it's going to be something bigger than 0, just bigger than 0, bigger than equal to 0. Okay. Plus some other properties, which is here. Metric on a space would be have for any 2 points, it gives you a number between bigger than 0, which gives you the so-called distance, but it needs to have another property, which is this. If you have 3 points A, B, C, the metric from A to B is less than going from A to C and C to D. In other words, detours cost you. So metric is positive or non-negative, I should say. Okay, one. And second, it satisfies the triangle inequality. Detours cost you. Okay. And third thing is that the distance of a point to itself, what do you think? 0. Now, when I told my son this a long time ago, long time ago, he was, I can't remember, he was like 10 or something. And I said, not everything's a metric, because I gave him an example. I said, look, suppose you are, oh, sorry, one more thing. You would like the distance from P to Q to be same as distance from Q to P. Symmetric. Right. Now, notice these axioms, they say nothing about straight lines, nothing. So we could think about a metric in the space of songs, if you could try, or a metric in the space of maybe economies, the distance between one economy and another economy, right? Now, these are not simple to do. As long as they satisfy these kind of basic axioms, then we have what mathematicians call a metric. So metrics already are very supple, very rich, very, very rich. But topology, I choose topology, is we don't need a metric. Okay. So topology, that's why we say, mathematicians say, topology is a set of structures. It's less than, this is geometry. It's less than geometry. Geometry is when you have questions of distance, okay? But more than just bare sets. And that's this notion of, now I'll give a name to this family. It's called the family of open sets. Okay, so let's go back and look at that. I should probably keep these drawings in order. I'll go like this. Okay, so let's go back to the family of open set. Why do I call it open? Well, here, suppose we have sets like this that just oscillating, just kissing each other. Right here, here's a point right on the boundary here. Where is it? Is it in U or is it in V? Well, it's in both, right? But it's kind of, isn't it? It's a bit precarious, right? This is point, if you look at it, if it's sitting on the, let's magnify this picture. Again, also magnify picture. Here's that point again. If it's sitting on what we think of as a boundary of this set, here's U, right? Then is it in or out? It becomes problematic. So we don't want that kind of case. We don't want that kind of situation. Well, and you probably learned this already in grade school when you talk about intervals of lines, but here, suppose you think of this boundary as not, suppose you take off that boundary, just think it like an orange, and you peel the orange, okay? Now you leave everything inside up to, but not including the boundary. That's what we call the intuition behind what's called an open set. This is intuition, all right? It's basically everything up to, but not including the boundary. But remember, up to, but not including, we don't have access to a metric. So we can't say how far you have to get, how close you have to get to this thing. You can't say, we don't have access to a metric anymore, right? The only concept we have to work with are sets and intersection and union. In fact, not all sets. Remember, this is defined for a particular family that has a particular, where its members satisfy these axioms of intersection, union, and covering, okay? Now, I could have taken this plane just to show you before I'll go back to the open set now, okay? Before I generated my open set with disks, but I could have taken this white plane here, R2, this is the Euclidean plane. I could cover it by these kinds of things. Lines. It wouldn't work actually. These lines are too thin. Well, okay. So let's try another way. R2, suppose I cover it by strips, two-dimensional strips. And they go out to infinity, by the way. Totally different from disks. Disks are compact, they don't go to infinity, right? But here, I cover this piece, this plane by strips that go to infinity. Okay. It's a lot wilder. Okay. And then if I want to generate topology out of this, I just say I had to admit into my family. It's called, let's call it curly G instead of curly F. I start with these strips. I have to allow intersections. So here's an intersection right here, right? I have to allow unions. So now you see some intersections are compact, bounded things. Some unions are go out to infinity. So this is a really much more ample or wilder kind of topology than the other one. Because some of its elements go out to infinity. I'm not even sure yet. You know, if I keep on intersecting and unioning, what do I get? You have to think about it. Okay. So the point of this is that you can define topology. It's not given by God. It's not given by some basic axiom. You can define topology. You can define it depending on the phenomena that you were interested in trying to understand. Songs, flows, economies, dances, what have you. Okay. As long as you have this family that satisfies this axiom. So it's extremely powerful. So topologists do this. What topologists do is they construct topologies on the spot in order to prove certain theorems. Okay. So that's really the beauty of mathematics, is you can construct structures, construct even axioms as you wish. This is what I mean by propositional play. Okay. Very powerful. Now, going back to this question, open set. Now the question about open set. Now, why do we call it open set? Because of this issue of the ambiguity of points on what would be ordinarily called the boundary. If we just peel off the boundary, we have intuitively the remainder of the interior. Okay, so but that's how do we get this? How do we define that more rigorously? Well, let's ask the question about the boundary. It's called boundary. Usually it's represented by, okay, this course is not about notation and memorizing formulas, things like that. But when I draw this, I mean the boundary of U, okay, this kind of del of U, okay? So, well, let's take a point on this putative boundary, okay? Remember, all I have to work with are open sets. Well, we can think about the open set, an open set containing it, all right? And then think of this, with open sets, you can think of maybe, suppose we just zoom in on this point. Zoom, 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 zoom. So now we have a magnified picture of it. If it's truly in the boundary, no matter how close you zoom into it, you're always going to see a little bit on the inside. And, oops, and some bits of on the outside, right? That's what it means for a point to be on the boundary, intuitively, right? Now, but remember, since we don't have a metric, I can't say what zooming means. I can say come in twice as close, 3 times as close, 10 times. I can't say that, right? So the way you define this test for boundaryness, is to say a point P. So we have a set is called U, okay? A point P is on the boundary of U if for any open set called K, all right, that contains P. So here's K that contains P. Okay, that's what I'm drawing here. Down here is in words. Okay, then K intersect U is not empty, meaning there's something in this intersection here, and K intersect the complement of U is also not empty. That means there's something out here as well, right? But drawing makes it obvious. But this, what I wrote down in here in notation, makes it rigorous. Okay? So this is how students learn. You draw pictures in order to understand the formal definition, but then you let go of the picture because the picture will be a chain. It's a step, but also it's a limit to your understanding. Because this definition is incredibly powerful. Then you can go use this definition to understand boundary for crazy sets, really, really crazy sets. I'll give you an example in just a minute. Okay, let me pause for a moment. Any questions so far? Okay. All right. Now we have now used open sets, the notions of to even make a definition of a new structure called a boundary, with no need to use numbers at all. So think about this for immigration. When people immigrate to a country, I used this example before. Think about what's called an alien. Normally you have this idea of people passing through the so-called border of the country, right, at certain checkpoints. But we know in the United States, at least, no matter even if you go 200 miles into the interior of California from the Mexican border, you can still be pulled up and treated as alien, right, according to certain criteria. So the border between citizen and non-citizen in the country is not the geographic border at all. Please. You have a question, Raphael?
Yes, we have two questions actually. We have one from Brenda, and we have Ivan with his hand raised up.
So, just say it. Say your question, please. Go ahead.
Okay, I'm just gonna read Brenda's question in one sec, and then I'm gonna pass the word to Ivan as well because they might be related. So Brenda asked us on the chat, can you help me understand the difference between an intersection and a union of sets? In the songs as example, nursery rhymes and songs sung in Spanish have a clear intersection and union that appear to be the same. Spanish nursery rhymes. Or is there a difference, or is this example incorrect?
Oh, right,
Brenda?
sure. Yes, absolutely. They can. Yes, absolutely. Intersection and union can be the same, for sure. Yeah.
Okay. Ivan, do you wanna ask your question?
Yeah, I think that my question is somehow different. It's about I figured out a certain metaphor about typology, and I want to know if I can think about it in that way. So the metaphor is that the topology is a sort of machine which can set which can define if something belongs to something or not. So it's not possible to define the boundary in some metric terms, but somehow we have a machine that says if a certain point is in a set or not. So it's just like simply yes or not, and not like more detailed answers. I don't know if I explained it clearly, but
first of all, the notion of being in a set or not, yes, a set can be defined. A set is always defined with some idea of membership, criterion for membership is in the set or in its complement, in the set or not in the set. Okay, but a boundary is not defined. A boundary is defined after you have that criterion. Okay, then you can define a boundary in terms of that criterion. Second point is that there's no machine. The whole point about all these definitions is that nowhere does it depend on computability. Nowhere does it depend on mechanizability. Okay, so these are actually notions which actually have nothing to do with finiteness at all. Okay. So it's very, very important. Okay. Very important. In other words, there's no finite procedure. You don't need a finite procedure, mechanical procedure. Just say there is or it's not some criterion. Some criteria can be mechanical, some are not. Most are not actually. Okay. Now I'll give you a funny example. Let's look at let's look at the rational points like 7/3 or 17/355. In other words, points of the fractions. Okay, where you have something in the form. Use a picture. I'm using a kind of P over Q, where P and Q are integers. Okay, rational numbers, fractions. Okay. Now, look at all the points. Let's look inside the square. Unit square 0, 0, 1, 1. Okay, this is 0, 1, and 1, 0. So these are the unit square in the plane. Consider all the points inside whose coordinates are rational. You know, like 1/3, 1/3. It's here, right? Or 2/3. I don't know. 117/355. Okay, so I don't know, somewhere around here, probably somewhere around here. Okay, how many points are there in this set? Well, infinitely many, right? You can just crowd them together. You can make these ratios finer and finer. Okay, now, so let's look at this funny set. I'll call that Q squared. Okay, because it's two-dimensional space. It's a two-dimensional region. Okay, but its points are only those points that have rational coordinates, not the real ones. Like 1/pi would be a funny point that's not in this set because pi is a transcendental number. It has no closed representation in terms of fractions. Okay, comma 1/e. There'll be a funny number. These are definitely less than 1, so they're somewhere in this region. But these are transcendental numbers, so can't represent them in neat fractional form. Okay. And now let's look at this set, okay, of rational points, rational coordinates in here. And I ask you, what's the boundary of this set? What's the boundary of this set? Anybody want to guess even before start thinking about it? There's anybody who hasn't taken the math course before in this. Think about the density of these points. All right. If you take any two rational points, okay, you can think about it in terms of the line too. Like here on the line, so it's 1/3, sorry, 1/3, sorry, 1/3, and then there's 2/3, right? But between them, you can fit another point in between, right? Just halfway in between. That would be another rational point. And then 1/4 of the way in between, et cetera, et cetera. So you can pack those points as densely as you want. But still, in between, you have infinitely many points that are not rational, turns out. Okay. Gives you a hint. So let's test this. Let's use the test of boundary, the criterion for boundary. Okay. Let's take an arbitrary point in the square. Okay. And we take an arbitrary neighborhood around that point. Remember, the test is if this neighborhood always contains an element of your set and an element, a point not in this set, then your point, the green here, is a boundary point. So let's try this test. Now I take an arbitrary region, okay? Now we know no matter how small we take this region, there's always going to be a rational point inside because rational points can be packed as finely as you wish. But also for any region around this, any open set around this green point, there are going to be points that are not rational. Therefore, this green point is on the boundary. But this green point was any point at all inside the unit square. Therefore, the boundary of the rational points is in fact the entire unit square. The boundary is not a curve. The boundary is a whole dense region. In the sense that here, the boundary is actually thicker than original set. The boundary is bigger, has more points in it than the original set Q squared. Crazy, huh? Feel like a magician.
Yeah. I'm gonna since you actually brought that up, I wanna go over two questions that are here on the chat, and also like if any of these questions that I'm reading, if the person wants to add something or like to do another rendition of that same question, just feel free to open your mic and speak. Yeah. So Rafael asked, how is it possible for a set not to have a boundary and be different of all other sets? And Nadia asked if there is a limit to sets in terms of time, if if we need to determine those sets at a particular given time or not.
Great. So here, I'll draw you two open sets, okay? One would be the set of all points at a distance from 0, 0, okay, 0, 0 in the plane, and all the points here, all the points that's points P whose distance is strictly less than 1. So basically, it's a unit. Try again. Here's 0, 0. I draw in dashed line the unit circle, and dashed line to mean I don't include the circle, but I include all the points inside. So there's all the points P of size strictly less than 1, right? So this is the disk centered at 0. Then I take another one. Take another disk, which is what was the question here? Not to have a boundary be different. Yeah, sure. Any set whose center rather, okay, any disk whose center is called C, all right, where C is strictly bigger than 2, means it's so far away that the distance between C and the origin is bigger than 2, means that it's not going to touch, right? Even if it were exactly 2, because it's an open set, it doesn't include the points right here at distance 1. Okay. Now, the question to be different from all of the sets is tricky because what I did here was different from all of the disks that are too far away. So yeah, I mean, I just drew it. It's easy, right? In fact, any set is compact like this, there's going to be all these other sets far away that don't intersect it at all, right? I'm misinterpreting your question, perhaps, Raphael.
No, Rafael just responded here, so I think it's a good
now
answer.
Time. The time question is very profound, okay? See here, these sets, again, the Pythagorean snare, I'd say nothing about time space here, right? These are just sets. So you can use it to describe occasions, places, songs, whatever, dramas, opinions, lives, right? So that's really key. It's really key. This is the suppleness of this kind of vocabulary. Okay. Later on, I will talk about time, but then you're introducing it specifically with a specific semantic. Right? Let's go on. If I can go on. Okay. Where are my topics? I think I used my topics page. Oh, here it is. Okay, sorry. Now, to give you some more grip, we talk about sequences, like sequence of what? And I think Bergson, and maybe it's Creative Evolution, he talked about the critique of cinematic thought, and in there, so one of you's rather can correct me. This kind of apparent unidimensionality of an analytic thought okay, or what do you call cinematic thought. It's not in the phenomena, but it's the phenomenon, but it's in the succession of acts of let's say observation or assessment. Okay. If you have a sequence of observations and assessments, that sequentiality is an artifact in the sequencing of the thoughts, not in the phenomenon. Okay. Draw a picture. Suppose we have the entire plane here, this solid place, and I start throwing pebbles into the water, okay? And I throw them one at a time. So here they are. Can you see the dots on the piece of paper? Do they show? All right, okay. So the first one, I suppose it's a pond, okay? It's not the open ocean, it's a pond, so it's boundary, okay? I start throwing pebbles in, or you can think of it as a dartboard, and throwing darts at the dartboard, okay? So it's a finite body, a finite region. Now, if you keep on throwing dots here into a finite body of water or dartboard, you would expect some clustering to happen, right? Some parts, if you throw infinitely many dots, intuitively you think, well, it could well be that there's some region here, some point, let's say, where many of the dots are clustering. You can ask yourself, is there such a point or not? Because you can try throwing it uniformly, right? But if you keep on throwing more and more and more, right, you're going to start packing in between the white spaces more and more. So the question can be, is there at least one point? Is there one point where there's a clustering so that infinitely many of your infinite sequence of dots are clustered near that limit point? What I'm trying to do is work toward a definition of limit, okay, limit, without using numbers. Because you see, one way to do this might be say, well, let's measure the distance from this putative limit point to my various brown dots and see if the distances start to cluster towards zero around this green point. But suppose we don't have a way to measure distances at all. Can we still define this notion of a limit point? And the answer is yes. Okay, and I'll show you how. And then we'll take a little break, a micro break, okay? So the way to do that is you take a region, and the question is, you need to test if this point P, and you have a sequence of points. Let's say we'll call them A1, A2, A3, AN, A infinity. Okay, the infinitely many points, infinite sequence of points, which you're throwing into your pond. Okay, can you see? Okay, and the question is, the test for P, is P a limit point? Okay, here's the test.
Xin Wei, I don't know if it's the same for everybody else, but depending on how your lamp is, I can't see the writing on
yeah.
the paper.
Yeah, maybe I'll turn off this light.
It's better now.
Ah, good. Less is more. Okay, good. So the point, here's the test. The test is the following. The test is take any region, any open set around it. Sounds like what we did with boundary point. Take any open set around it. Okay. For all open set U containing P, all right. Ask yourself if are all the AIs inside U for I bigger than some big number. So that means that if you throw away the first 100 million of the A's, are all the remaining A's inside that region or not? So that would give you intuitive this idea that after a while, they all start to cluster around here. This is not entirely precise yet, okay? Not entirely precise. The precise way to say is, after throwing away a finite number of your A's, because these are kind of the outliers outside here, okay? Then can you say that beyond a certain index, all the subsequent points in the sequence are headed toward P, are inside this region U. Now, the key thing is that this test I have to apply for every open set. See, this is the test for every open set. So I did it for U, but now what about for another set? So I have to do this again and again. I do this for another set, this pink set, V. Can I still apply this criterion? So maybe it's a different set of A's I have to throw away and a different big index, not N, but N prime. And then say, okay, after throwing away a finite number of those points, sequence points, and then if I look sufficiently far out into my sequence, subsequently, those remaining members of my sequence do cluster around P again, inside D. Sorry, I should say inside D. So I'm going fast here, but you should, if you want to, you can go back and think about this criterion because it's carefully stated. This criterion is you have to test this for every single open set in your family, in your topology. So that topology, that way of testing for every open set is what stands in for zooming in. There's no notion of zooming, right? Because we don't have a notion of distance anymore. So replace the notion of zoom by this criterion for all open sets containing P. In other words, for all what's called neighborhoods of P. All neighborhoods. Right? Because you see, if I pick a big neighborhood, right, it'd be very fat around P, I'm not really gaining any quote resolution, right? Then if I pick P to be the open set to be the entire space, this is the space X after all, right? Entire space X, then okay, of course, automatically the criterion holds. So that's not really a very stringent test. But if I say it's true for all open sets in my family, that's a pretty stringent test. Right? Not only true for this big set here, but true for any quote small open set containing P. But remember, there's no notion, there's no notion of small. All right. Let me pause here. Okay. All right. Can we take a 3-minute break because there's more concept, but give you a chance to set just to see where we are in this set of ideas I'm introducing today. Can you see this? Damn. Okay. So I want to talk about limits. Now, after the 3-minute break, I'll come back and we'll talk about transformation. Okay. Remember, all this behind this is also trying to come back to this idea of process and later in next week, yeah, the individuation and process without having to think about numbers and metrics. Okay. So we take a little short break.
Okay.
Alright.
Xin Wei, just one quick thing. Can I ask you to, because I see that there are two users you're using. There's one which is like just with the video, and the other one that is sort of like your drawing board is with the video and the audio. Can you switch? Like, is that a possible thing with the setup that you have right now, so that the audio comes out of the your own image?
Yeah, I'll try. That's on my phone.
Okay,
So.
yeah, I say this because it makes it easier for the recording, because I'm having to sort of like live edit and go back and forth, and then if the face and audio are in one place, it's just easier for me. But if you cannot, I'm here anyway. So, but if you can, that would be wonderful.
And when we come back after a 2-3-minute break, Josh can ask you a question. Okay. All right.
Yes.
Point.
I can let Josh speak as well if needed. Okay.
Thank you. So Josh's question is the points implied discretization or abstraction of reality. We should go back to the examples that I mentioned before. And here. Again, this is why I mentioned the thing about the Pythagorean snare. Remember, one of the examples I suggested was thinking of a river, here the banks of the river here, and then we want to understand, what we can try to understand is the so-called topology of all the flows, all the way the water flows in this river, okay? I'm drawing lines on this river, okay? But that's just because those are the trajectories that the leaves trace when I drop the leaves into the water, and then I use the leaves trajectories as an indicator of the flow of water. But the flow of water, the water is an extensive medium. It's continuous extensive medium. So it's in fact, a three-dimensional volume of flows. So that's a plenum, in fact, actually, a plenum. So when we talk about topology, we can topologize the flow of a plenum, right? In that case, we can, inside the plenum, think about, for example, elements of the space of curves. Here, a topology could be, you could say, is the space of paths in flowing water. Okay, this could be my topological space. Okay, and each element is not a point. Each element is a whole infinite, continuous streamline, right? Another possibility could be that M be the space of all economies. Economies. In fact, mathematical economists do this. Space of all economies, which is by no means a point anymore. Each element here is an economy, a whole economy, right? Et cetera, et cetera. So again, I would be careful when we say the word point in this case. Point, so we want to be careful not to think of point in the geometric sense of point. Okay, I should say element probably. But still, the question of possible reductiveness comes into play, because I have to think about, that's why I say there's an art to the topology, to topologize in a way that doesn't, that is adequate to the phenomena or to the aspects of the phenomena in which we're interested. Okay, that's why it's really important to be able to design the economy. Okay. Okay, maps and transformations. So if we have two topological spaces, that means that we have a set, and then we have a notion of its open sets, and then we have another set and its open sets. Okay, G. So for example, what can we say? So for example, we can say that this first M is basically the plane, flat two-dimensional plane, but N can be maybe the space, R3. So then we can think about all these different ways we can take this flat handkerchief, for example, and throw it into space. So it becomes some like, think of this as a piece of silk. M is a piece of silk. And we can throw the piece of silk into the air. So it then becomes a surface with all this complicated structure to it. Okay. So that throwing into the air, we can think of this as a mapping, which I'll call phi. Synonymous, you can call it mapping, transformation, okay, which maps from points in the plane into points in space, okay? But mapping can be much more wild than that. It could be, for example, maybe we take this, this is a piece of dough. This is dough. And the mapping can be like a baker's map. If I take this, I'll do it with a piece of paper. Let's say this is a piece of dough, like this. And imagine this is a piece of dough. And the mapping can be the following. I fold this dough over, I roll it flat, and I take a roller and make it out, stretch it out again to be the original size, make it flat. And then I fold it over again and roll it flat and stretch it out and roll it again. But each time I'm actually rolling it out flat, so it comes back to the original size and dimensions. And if you make pastries, this is how you make, mille-feuille, how you say it, 1,000-layer cake. You fold and fold and fold. This is called the Baker map. Okay. So this mathematician is topological, call this a topological map. It's a certain map called a Baker's map. Okay. So that could be a mapping, right? Or it could be a rather destructive mapping. Here's a mapping. I take this region and I cut holes in it. So this would be what you would think intuitively is a non-continuous mapping anymore. So mappings can be all sorts of transformations. But let's just take now this idea of a mapping from one kind of space to another kind of space. I'll implicitly include inside each this idea of they have their own topologies, they have their own set of open sets. Because remember, here, if it's a three-dimensional space, the natural open sets would be spheres. not disks. Here, the natural open sets would be disks, right? Flat disks. But here, the balls, you need a chunk intuitively, okay? So the topologies are really quite different in the plane versus in R3. Okay, now let's go back to now the general setting. If we have a mapping which goes from one kind of space to another kind of space, we'd like to have some intuitive idea about when is this mapping nice and continuous. That doesn't do the kind of cutting holes in it in the shape, nor does it talk about folding into sharp creases like this, you know, or that's still continuous really. Going like the rip like this, that would be not good. Right? That's not continuous. Okay? So one way to think about that is think in terms of what happens to points inside here. Let's say here's point x1 and x2, and then see where they go. Phi of x1, phi of x2. Okay, there are 2 points in the domain. This is called domain. And under the mapping, it goes to some target or range space, and they got mapped to somewhere here. Suppose in domain is my plane, and suppose now I draw a particular shape. Let's say a donut, you know, like a solid, something like this. So 2 points here, and they get mapped to some points here and here. Okay, so this is P, this is x1, this is phi of x1, and this is x2, and this is phi of x2. Okay. Now, one way to think about is to think about the violence or the gentleness of the stretching that's happening, right? So you might want to compare how far, if you had a metric, phi of x1, the distance in the destinations, compared against the distance where they came from. Compare these two numbers. This is a distance in the target range, and this is distance in the domain. But remember, I can't do this if we're talking about topology. There's no metric here. This is what you could do if you had a metric. So you actually could compare distances. And then you can compare and say, well, you know, if I want to guarantee that this distance is not too big, if I can guarantee that by saying, as long as my initial points are small, it's close enough together, then I can find a way to guarantee that the targets don't get too distended. Okay, I'm not going to go further this way because this is all very intricate and really messy. Okay, here's a much more subtle way of defining continuity. It goes like this. Remember, all we have available to us are this idea of open sets in each case. The open sets of M and the open sets of N. This could be any kind of space of songs, and this could be people who are singing, or it could be people over here and their, you know, quality of life, however you want to measure that. Okay, all right. Or it could be, okay, that's enough. Now, or it could be age. You know, here are people, and this could just be their age, you know, or their income, some numerical thing if you want. Okay, to make it concrete. Now, the way you check for continuity is the following: is if you have an open set here in the range, here. So this is your surface, remember. I pick an open set inside. This is K. I look at where it came from, back over here. Meaning all the images, all the points back here that landed in K under this mapping phi. Okay. In other words, I look at what's called the pre-image of K. Pre-image of K. This symbol here, phi to the -1, like inverse, okay, is look at all the points in M such that phi of x is in K. Now, this is a formal definition, but intuitively, you think, where did K come from? Look at all the points back in M that landed in K under this mapping phi. this set is inside M, right? This set is open in M. If, in other words, I take any open set, I'll repeat, any open set K in here, if its pre-image is also open back here, then my map is called continuous. This is homework, okay, to think it through. It turns out to be incredibly supple. This definition actually is the same definition as this kind of definition when you have metrics, you can compare stretches. It's amazing, okay? But this definition of continuity is a lot more powerful because it doesn't have to say is it finite dimensional, infinite dimensional, are these spaces of songs, spaces of people, whatever. As long as it has a notion of open set, we can have a definition of continuity. Incredibly powerful. All right. Now to recap, we have now a way to think about boundary in terms of open sets. We have a way to think about limit point in terms of open sets. What's the limit? And now we have a way to think about continuity, this idea of bending and stretching without breaking something in terms of open sets. No numbers were needed. Okay. Now, I'm going to, I know I'm running a little bit, but I want to get to a place now where we can have a theorem in mathematics. See, because mathematics is not just definitions or concepts or objects, okay? That would be kind of merely a structuralist approach to things. But also is what can we say about these kinds of patterns and structures and transformations that's true, that's provable, okay? And one of the most fundamental things that we might want to show is if you apply two continuous, I need something soft. Okay, well, I'll just use this one. This is my silk handkerchief, right? So here's one continuous transformation. I just roll it up, right? Another one is I can fold it. These are continuous. Another one is I can go like this. These are all continuous transformations, turns out, but they're quite different, right? Or if this is a rubber sheet, I could fold it over and stretch it out like the baker's mat, okay? Now, what if I take two such operations? First I roll it up into a cylinder, and then I do this, right? Is the composition of these two continuous maps a continuous map? I'd like to say yes. Yeah. All right. So how would you prove it? Well, there's the theorem. This would be our first theorem, okay? If we have three spaces, M and let's say P, okay? Each of these is a topological space, like space of people, I don't know. Oh, this is the planet Earth, let's say. And this is a space of weather systems around the planet. And P is a space of, let's say, temperature and pressure around over the surface, okay? Now, suppose we have a transformation which goes from geography into weather systems, and another transformation that's called mu for measurement, okay, which goes from weather systems to measures. Okay, so these are two transformations. And suppose each of these is continuous in some intuitive way. Oh, no, sorry. Suppose you can define intuitive. Oh. Before we go there, better recall how we define continuity. Continuity is the following. If you have just two spaces, a mapping from one to the next, okay? Like from the planet Earth, we look at the geography of the planet, and then the mapping is going from the geography to the weather systems on top of the geography at a certain moment, a certain day, let's say, okay? And each of these has a notion of openness. What does it mean? In the case of the planet Earth, right, that would mean for the just geographic region. Like you could use some intersections of circles, disks again. Okay. In the space of weather systems, it's different, right? It would, let's say, weather systems, Earth. surface. This is considerably more complicated, right? You have to think about, well, what is a weather system? It's a flow of air, it's a humidity, temperature, pressure, blah, blah, blah. You know, it's a very complicated set. But suppose in each case we have a notion of region, a notion of open set, that they're similar. You can say similar weather systems are similar to one another, or parts of the Earth that are close together, let's say. And given those two respective topologies, we can define continuity in the following way. For every open set in the target, this is the target, and this is the domain, or range, sometimes you call range. Let's not be so militaristic. In the range space and domain space, okay? For every open set in the range space, its preimage is also open in the domain space. That's the definition. In other words, open sets came from open sets. It's head twisty because they had to look backward. Okay, but let's apply this definition to proving something. That is the following: if you have three topological spaces now, and you have mappings between each of them, and they're both continuous. So say phi is continuous, map from n to n, and mu is continuous from n to p. Notice these definitions had to rely on the respective topologies, okay? Then the composition, first apply phi, then apply mu, is continuous as a map from m all the way to p. In other words, first you apply phi, so it gets from here from m to n, then you apply mu, which gets you from n to p. So this whole map is the composition of two things. First do the phi, then do the mu. That's how you write this down. First apply phi, then apply mu. That's what that means. Which is kind of a very general version of what I just did. I say rolling is continuous, crumpling is continuous, therefore the composition of those two operations is a continuous operation. Okay. Now, how would you prove this? When we do, it's extremely beautiful. It's very short, very, very short. Here's the proof. What's the test for continuity? Well, we have to pick, this is now a mapping from m all the way to p. I'm skipping over n, right? So this is draw it out in pieces. Here's the mapping from m to n is phi, the mapping from n to p is mu, and the composition. It's composition. So what I do, I take a look at the destination, right? I pick arbitrary open set. Let's call it K inside P. I need to check that it came from under this composite map, an open set in M. How do I do it? Well, it's a question. Is the inverse of this set K open in M? Question mark. If it's true, then I'm done. I do it in two steps. First, K is an open set in P. I know that mu is continuous. Therefore, the inverse image of mu of that set is open in N because mu is continuous. Now I have an open set inside N. But because phi is continuous, that means phi inverse of mu inverse of K. This set here is now inside N, and it's open. Because phi is continuous, we know that this is open in N. But this is exactly the preimage of this composite map. Because by definitions, everything that goes from here to here to here is in fact what I need to find. So that means I've proven already that this composition is continuous. I know I'm going really fast. Okay, I'm sorry. But this is a 3-line proof. It's amazing. Imagine if you had to prove, for example, let's say you have two functions, sine of x, f of x is sine of x, and you have another function, g of x, or g of y, let's say, is y squared plus 27y plus integral from 0 to whatever, t of y squared, da, 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 da. And to prove the composition of f g is a complicated function, satisfies some epsilon delta group. It's crazy. It's crazy complicated. Right? This is incredibly supple. Don't need to know anything else except that these are topologies. Okay. Now,
Xin Wei, I wanna. There were two questions after you did a short recap of the concept of continuity, right? There was another follow-up question from Ricardo that was about what's the relationship between an open set and continuity. And there's another one from Rafael, which was what is the difference between the concept of continuity and transitivity? There's also one from Yana about the relation between continuity and difference, which I think might I mean, it's three questions, but I think they might sort of come together in a way.
Let's do this. Let's talk. First one about continuity and transitivity. What I just did here, this theorem, one could say that's transitivity. All right, so transitivity is more like a relation. It's basically something you can say about relations. I wanted to bring it up because of the question. I'm sorry, who asked the question about identity? A equals B, right? And I was going to come to that later on, but I think we have time. Okay. So this idea of relation, okay, which is whenever you have two spaces, let's say M and N, let's say, and here's a space of people, let's say, here's a space of here's the Earth, M is Earth, and N is weather systems. Okay. Or something else. So this M could be people and N is songs, let's say. A relation is basically a pairing of an element from M and an element from N. Okay, extremely general. So and then this is a set of objects. So it's a set of all such things. Sorry, a set of such things. Okay. It doesn't say how you do it, just that if you have a pairing, that's a relation. Mathematical relation. It's extremely general. Now, an equivalence relation. Okay. This is relation. The equivalence relation, let's call it, let's write it differently. Let's call it like this with a squiggle. Okay. It's a particular kind of, these are called binary relations, binary relations, okay? Binary, because only two of them, right? It's a particular kind of binary relation with the following properties. One, P is related to itself. Second, P related to Q is the same as Q related to P, right? And three, transitivity. If P is related to Q, is equivalent, we should say equivalent to Q, and Q is equivalent to R, then P is equivalent to R. This is the transitivity rule. These are the three axioms for what constitutes an equivalence relation. Now notice, this is not the definition of continuity. Continuity has a notion of mapping, okay? All right, we could probably cook up some relationship, but these are really defined separately. Okay, so really the question of continuity is independent from the question of transitivity. Okay, formally, I mean, only. Now, I want to make one point though. Okay, just want to finish. This question about last week about A equals B and all that. You see, this is the difference between a propositional way of doing mathematics versus a kind of metaphysics. See, it would be a metaphysical argument to say that we have some sort of how do you say, an external or transcendental principle of identity, let's say, to work with. Here, instead, what it is, mathematicians take the properties of what makes a relationship, an equivalence relationship, and it makes them explicit. So in other words, these three properties are what characterize what you would think of it as an equivalence, right? And we call them equivalence relationships. Not every relation is an equivalence relation. So that's why in mathematics, it's interesting to actually, when you make that explicit, and then derive consequences from that, which I was going to do, but I don't have time today. Okay. I drew a picture last week about that. All right, sorry, you're going to say? Continuity and difference? Continuity and difference and difference. Okay, the question from Yana about continuity and difference. Also there, you see, the beauty of the situation here is that we don't have yet a notion of difference. Because as Jana probably saw, I mean, if you say difference, you need to have some way of thinking about, x minus y, this question, the minus, right? How do you make a difference? We don't have it. Okay, we have intersection, but we don't have difference. And that's quite profound, actually. See, this is an operator. The operation of inverse, additive inverse. So it requires that, or you can have another notion that basically, anyway, we're not going to talk about manifolds today, but the notion of difference, okay, difference and differential, think of Deleuze, right, repetition of difference, right, it makes a big, these are additional structures beyond topology, okay, beyond, it's more structure. So this is more primordial than that. It's even before difference. Okay. I want to check the time because, oh wow, we have 1 more hour. Okay. And yes, right. Yes. Okay. Can I draw some more pictures? Okay. Can I go on? Yeah. Okay. Oh, is it allowed to do a mapping of complexes? Oh, yes, absolutely. Then it has a nice question. Is it allowed? First of all, in mathematics, you're allowed to do anything. It may not be provable. It may be false as a theorem, but you can always conjecture it. Okay. That's the fun part of mathematics. You're allowed. Of course, you're allowed. Because we're not acting under the sign of truth in terms of where truth is. Truth means in accordance with empirical fact. Okay, we don't act under that sign. Okay. In fact, mapping of complex sets is very. I was gonna go there actually. We haven't defined what compact means yet, but we will. Hopefully, we will today. Okay. Now I'm going to talk about this notion of connectedness. Connectedness. So think about this. Connectedness. This is a connected piece of paper, right? But if I do this, it's not connected anymore, right? So we want to formalize this notion into a way that can make sense beyond just pieces of paper. So when we do it, and remember, all we have to work with right now is a topology, meaning a family called open sets. So suppose we draw on this piece of paper a disconnect, what we would think of indubitably a disconnected segment. Okay, well, how would we do that? If we were in the same room, I would play a little bit and ask you all to think about that. But let's just say, and remember, let's say for now, the open sets are the open sets which are the topology is one generated by open circles, by disks. Okay, so here's two elements of my topology, which I by magic pulled out of a hat. And hey, look, I neatly wrap each of those two segments in two different open sets, which are disjoint. So I'm able to detect, so to speak, the disconnectedness by doing this. But of course, you could say, well, I could have been unlucky. I could have chosen maybe this open set here, which actually contains those two in the same open set. So it doesn't quote distinguish the disconnectedness of those two segments. So the definition of connectedness is the following. Not that every, just that you can find some pair. A set K inside my domain, my topological space M, okay, subset, this is what it means, is connected if you cannot, it does not exist, two, you know what, let me make it easier. I'll define the opposite. Disconnected. Okay. A set K inside M, any subset, okay, is disconnected if you can find two open sets. Okay. There's one, there's the other. Two open sets such that the union of the two open sets contains K, because they cover K, and the intersection is they don't meet each other. Done. See, it's very elegant because I didn't say anything about the shape. I didn't say anything about how big they are. All I need to know is that do they cover the set K? And can I have two of them that don't meet? So I've disconnected them. Now this set K could be crazy wild. This could be K. No? It could be just crazy cut. If it's in space, it could be flow lines in a river, it could be songs, okay? But connectedness can be tested very primordially this way. Can I find two open sets that don't meet each other that together cover the whole space, the whole set? If I can, I've shown that it's disconnected. And a connected set is that for which this is not true. Meaning, here, I'll draw a connected set here. See, now if I try to cover it by open sets that are disconnected, see, here's one, here's the other. These two open sets are disjoint from one another, but because they're disjoint, they're omitting this gap here, right? Right? If I want to try to cover that up, that means I have to draw something like this. V has to overlap with U. There's no way I can make V and U disjoint and still cover the entire connected set. All right. Now I've drawn pictures, which makes it seem really simple, but then really should go back and think about those examples. So the set of all economies, the set of all songs. Okay, then it becomes really interesting and powerful. Questions so far? Besides the compactness. I'm going to prove the theorem now. See, if I take a connected set like this, and it's suppose this is a white paper, it's a rubber sheet. Okay, the intuitive idea for continuous mappings is to be able to crumple, stretch, curl. Okay, these are canonical geometric continuous function mappings, right? If you draw this on a piece of rubber sheet, and no matter how you stretch it, this curve should still stay connected, right? So it gives us the idea for a theorem, which is if you have if K is a connected set in the topology in M, okay, this is the theorem, and phi is a continuous mapping from N to N. You know where I'm going, right? Then phi of the connected set is connected in the domain. In N. Okay. Now, it could be really wild. Okay, so for example, all weather systems. Think of the weather systems on the planet Earth, right? And then maybe the mapping is you go from the weather system to temperature and the pressure, let's say, at a certain station, weather station. Okay, but all weather systems, all possible weather systems. Okay, if that mapping is continuous, then you think about like morphing from one weather system to another weather system is, let's say, a connected set. If you say that, then no matter how you take measurements, those measurements, the readings you get out will also be in a connected set, which makes sense, right? The temperature don't just jump. Okay. Okay. All right. So now let me go. How do you prove this? Well, we need to check that this. Okay, this is M, and N might be some funny, and M is something else, whatever it is. And I think of a set in here. This is my K. All right. And phi of that is some image. I don't know what it looks like. Okay. But I do need to prove that this image is connected. Okay. So, right. Okay. So remember, if it's disconnected, right? If it's not connected, right? Suppose it's not connected. I need to prove it's connected. So I try to say, well, what if it's not connected? Suppose the image here is disconnected. Okay. The opposite. What would be true? Well, in that case, I could find two open sets U and V, right? They don't meet, and they completely cover my image. Then there exists two open sets, U and V, open in my target manifold, target space, such that U and V cover the entire image, right? And they don't meet each other. They're disjoint. Okay. Now let's go on. Let's take those two sets, they're open now, right? And pull them back to M under my mapping phi. So here's my image space. Here's my funny set U. Here's my other set V, which disconnects my image, right? Because phi is continuous, remember, that means U came from phi inverse of U must be open inside my domain, and phi inverse of V is also open by definition because phi is continuous. But look, now I have phi inverse of U and phi inverse of V are both open in my domain. Aha, look. What about the union of those two? The union of those two, let's call this, yeah, just call it, it's called U tilde, U bar and V bar, okay? It turns out, if you look at it, think about it, the union of these two sets is everything that got mapped from phi into my image. So this covers my entire domain K. And these two, they have to be disjoint. U bar intersect V bar has to be disjoint. Because if they weren't disjoint, that means they have a point in common. If they have a point in common, that point would map under phi into a point in common between U and V, which I assume to be disjoint. Therefore, my supposition that this is disconnected here is false, which is what I wanted to prove. And so the opposite is true, it's connected. So I'm just giving you, this is a very, very short proof, okay, tiny little proof, okay? But I want to go through a little bit because people usually, when we talk about mathematics in philosophy, whatever, see, in mathematics, the real work of mathematics is this kind of thinking. It's not about drawing pictures or writing a definition of a structure or measuring something using a mathematical structure like a matrix. It's this. this kind of reasoning, and this kind of playful reasoning, which is supple, right? And can accommodate very elastically all sorts of phenomena and situations. Okay. I'm not going to make this about proofs. That's not what the point of this course is, okay? But I do want to go through and show you, even with the most minimal set of concepts, we can now prove things, you see? And this does not depend on data, does not depend on algorithm, does not depend on a machine, and does not depend on empirical fact. Okay, it does depend on axioms, and depends on what you want propositionally to be the case in terms of as your ingredients you want to work with. So you can fictively change those axioms to something else, hypotheses to other fictions, basically. But it does involve proof. So subject to those suppositions, what can be proven? This is very unique to mathematical thought. Okay. It's not philosophy, not science, not fiction, but it's a unique mode. Okay. All right, let me pause. Yeah.
Yeah, Xin Wei, we got a question from Nahla. She was asking if there could be an example to this part, like the other one you did on people and age, using people and age.
Yeah, sure. Yes. I'm thinking about that. I'm thinking about, like, I don't know, this is going to be, I mean, you all can come up with much richer examples. Okay, I'm just using some simple pedagogical examples. So, for example, drinking age, and let's say drinking age and age for service, military service. Now, what are they? 18 and 21. I can't remember. Voting age? There's a discrepancy. Okay, so. It depends on the country, it depends on where you are, right? Let's just say that you can't drink in certain states in America until age 21. But let's just say that you can be conscripted for the army when you're 18. Let's just say, okay? So the discrepancy. But you can ask this kind of question. People. Okay, and then drinking, can drink or serve in the military. Okay. So you can say here's a criterion. So here's a mass of people, and there's a criterion for this. If age of people is bigger than 21, let's say, right? And you can ask, or you know what, driving might be better because it's an interval. Let's say driving. There we go. Okay, so let's say age of P is bigger than minimum age of driving. Let's say 16. Okay, but less than, suppose it's a maximum. Suppose, I don't know, 70. Okay. I have a few more years to go. You can ask, does this include or not include the boundary points? Is it strictly bigger than 16? Or equal to 16. This is very nitpicking, right? But if you get into accidental legal issues, that doesn't matter, right? So in other words, is this interval, for example, closed on this end, open on the other end, or what? Is it doubly open? This is an open set here, right? Strictly bigger than 16, strictly less than 70, okay? This would be an open interval, okay? And if you include the endpoints, up to including 17, this would be a closed interval. So then you can ask about various kinds of operations. This is probably too simple. You can say, all right, suppose we implement some changes in technology with more self-driving cars. Does that change the ranges of people who should be permitted to be in a car or not? And how does it change? Okay, you need to elaborate this example. This is not adequate. Okay, but I'm trying to start the ball rolling by saying start with people and maybe use some simple target spaces, either age or social classes. Okay, that should be homework. Okay. I'm looking at the time. I'm sorry, but I think that maybe. Oh wow. Okay, I want to. I'll show you what I want to offer up in terms of concepts, and then you can decide later on what we want to come back to. So I want to talk about, also set up some notions that would be helpful for the metabolism and individuation topics as well. Okay, one of them is the notion of density, which is related to this earlier part question about, we had lots and lots of points clustering up. Okay, and what does it mean to say they're really dense in some region? Okay, remember, I don't know if I talked about it, this notion from theoretical biology of extended criticality that Giuseppe Longo and Monteville and other people have talked about. I'm thinking that there's a way to extend that notion of extended criticality using the notion of density. So I really do want to introduce this definition, this notion, this concept. Okay. And then another notion would be the notion of compactness. I think somebody asked here already about compactness. Okay. And this is a very special notion, which it doesn't come from the dictionary definition of compact. Okay. Well, but it's actually even more powerful than the notion of connectedness. And you'll see why. It allows you, for example, to basically go between local and global. So all this debates about locality, global versus local features. I think there's a way to understand them. Well, there is a way to understand to connect global and local using various notions. One of which is the notion of compactness. Okay, and topological compactness. So I think it's very important to think about that. And then I think that would be what I would like to do for this first introduction to topology. Later on in the course, and maybe a different course, is we want to meet up with Deleuze, for example, Gilles Deleuze, and his notions of multiplicity. Then we really do need to be furnished with more concepts from, in this case, notion of a manifold or topological manifold. And then earlier this question of difference comes into play, because manifolds can be topological manifolds or can be manifolds with what's called differentiable structure, the idea of a difference, but the difference is no longer Euclidean. So that's really important. And then the notion of a flow, which will equip us to be able to talk a little bit about potentiality and actuality, both in the sense of what Deleuze might be talking about, and also Simondon in terms of individuation. Okay, so maybe this will have to come when we go to individuation, because we don't have time today. All right, but there are more concepts that will be, useful for approaching these notions.
Xin Wei, just before you proceed, I just want to two things. One more logistical. Can you just move a little bit to the side just to re-centralize on the camera, like the camera pointing to your face a little bit? Yes, thank you. And it sort of accompanies with the writing. We were talking about like the body following along. It does a big bit.
All right.
Cecile also had the microphone open, and I wanted to ensure that if anybody has like any question before Xin Wei proceeds.
Please go. Just speak up. You don't have to wait for reading the
Yes.
text. You can just speak up. I'm looking through this chat though. I think we covered points. Density.
Yeah, we're up to date with the chat, yes.
Okay. Density. So
I might also say, Xin Wei, you are very welcome to take a 5-minute break to get a cup of tea or grab a glass of water or something. Just thinking of you here.
Yeah.
For the hour. There's so much to talk about. Okay, 5 to the hour. Yes, maybe we have a 5-minute break until the hour, and then I'll think carefully about how much I would do, because I think I'll probably need to switch to metabolism now. Yeah. Okay. Murder your darlings. Okay, we'll come back.
Okay.
So just check in. How are you guys holding up? I mean, this is probably pretty abstract, but how are you guys holding up? Just check in with you. You all. I think the real absorption would be when you are able to go back and look at the notes and furnish. It's like reading philosophy, right? Also, or Simon Dono, for example, anybody to furnish the discussion with your own examples that are concrete. So that would be great. Drawing pictures are fine, and it's fine, but then later on think about less visual examples. Okay. All right. And if you go to Discord, I'm happy to check Discord and carry on the conversation to elaborate. Okay, shall we continue? I have one more notion I want to introduce from topology, or also, by the way, it's not just topology, but we'll call it topology just for brevity's sake. And then that is the notion of density, and then we'll just switch to metabolism. Okay. So this question of density. Remember already, I introduced this idea of rational points. The points whose coordinates are both rational, right? So and that set, first of all, it's infinite set, okay, infinitely many such coordinates, and they're very, very dense. They're kind of very fine, it's like spraying onto it. And no matter how closely you look around such a dense point, such a rational point, there are infinitely many points that are not rational around it, no matter how close. So it's very, very packed. So it's densely distributed through the entire square. So it already gives you some idea of density. So density, we can actually turn this pretty much into a definition. See, a subset, not just this set, but any subset, okay, inside the space M, okay. How do you test its dense? Well, say it's dense if you do the same thing, right? You zoom, right? But by saying for any, let me do this. Yeah, right. Any open set. Sorry, hang on. If for any point in this putative set you want to check, okay, and for any open neighborhood of P, meaning an open set that contains P, okay, neighborhood for short, okay. This neighborhood U meets your ambient space. No matter how much you look, you're still gonna get elements of this ambient space contained, no matter how close you look. Okay, that's it. Now remember, you can think about certain things. I mean, for example, in social sciences, I mean, people talk about immigration and boundary and in a more theoretical way, right? So like what's called border studies, this kind of thing, and we know questions of identity do not line up neatly with either geographic boundaries, nor with institutional boundaries, the formal boundaries of an institution. Okay, so I mean we can elaborate this quite far. And then you can ask various questions, which we don't have time to go into now. Right? But that's just the beginning of the conversation. So that's now in terms of how I want to use it later on. It will come back when we talk about in the very next half hour now. When we talk about critical points for living system. Okay. So let me roll forward, if I may. Any other questions? Now, to switch to a different modality, I'm going to show slides at this point. And with this is Zoom. Here we go. Sure. Sound metabolic. Okay. Yes. Here we go. Can you all see the slides? Yes? Okay, great. There we go. Hopefully it comes back. No, let's try again. I interrupted it myself. Show slides, metabolic. There we go. Can you see the features of biological life? Yes? Great, okay. So a lot of this is coming from, for example, work by Stuart Kaufman and Giuseppe Longo, Mel Monteville. They're in your readings, okay? But I wanted to point out half a dozen or so really, really key features of biological life that has emerged in these discussions, okay? Among them, for example, I mentioned this thing about this notion of extended criticality, which is actually related, I think, to the question of metastability from Simondon. Or this idea of that living systems create order or create structure. And most importantly, the last point about the indeterministic aspect, indeterminism of living systems. Okay, so there's a lot we can say about continuity, which is a proposition. Again, you see, in all these things, the approach I want to take is not in terms of a metaphysical theory or a scientific theory. It's really more about a propositional approach. What if we pay attention to the continuousness of behavior, of life, of development? What new insights can it afford us? That kind of thing, right? So Longo and Piney point out in this article about external criticality and structural stability that in terms of the material operations of the organism, okay, is continuous. And in fact, it depends on, it cannot be disassociated from the metabolic, physical, thermodynamic work or operations that are happening in the medium. Okay, they say it better here. Okay, so this kind of irreducible materiality, which we can go down even further if we want to go down to the quantum mechanical level, which we see in biological life. Okay, and to continue that, I wrote it out so it's a bit more. For this part, forgive me, I'll just read because it's better written here than I can say it at this point in my jet laggedness. The morphological development of the organism, okay, is inevitably as a function of relational and extensive relations, okay, as well as intensive dynamics. And the resonances at play between physical processes and hormonally mediated coordination of metabolic processes that are different. They're different according to, for example, the spiraling of a tendril of a climbing plant in open space versus a tendril curling around the physical affordance, like a twig. These processes are in turn catalyzed by an elaborate set of organ structures at multiple scales, from intracellular to whole organism and even biome scales, that are reflexively the morphological and structural result of metabolic development. Okay, so it's not just geometry. To drive that point a little bit more, on the left-hand side, you see this is using molecular tracking of the membranal, the changes in the membrane structure within cells, inside cells. Okay, this is what I call the wet dynamics of a cell. None of which is really captured by, for example, A-life type computational models. And to be playful, we can think about how to transport that kind of idea of the flow of membranes within a cell. The membranes of a cell get absorbed and reformed and then taken up in other organs inside the cell. It's really amazing. Okay, so that made me think about, for example, the petric dynamics, the dynamics of stone in Middle Age medieval England's towns in England. And anyway, no time to go through that today. But this idea of flow of matter through structure is really quite interesting, quite evocative, I think. Okay. Speaking of flow, another notion, another aspect is continuity. And remember, we have topology to help us. Okay, so thinking about maybe it could be interesting, I propose, to think about continuousness of analog materials, of analog matter, of analog processes. Okay, I won't have time to go through that today. 3, a really important aspect, and truly really important, I want to come back to, is this notion of criticality. And next time, okay, maybe next time, we'll see. I'll use this as a figure of thought, but it's not the actual, this is just a kind of a rhetorical crutch, okay? This hill, this set of hills, you can think of not, this is really key. Do I have a figure for that? One should not think of this as a picture of the physical configuration or social configuration, okay? Not the actuality in that kind of mechanistic sense, but instead think of this as extended notions of energy and a kind of a generalized thermodynamics, okay, in energy, which one can design. This is another key thing. You can design your own notions of energy according to what phenomena you want to make legible. It's really crucial. So don't let some scientist or cognitive or whoever tell you that this is the energy functional for blah, 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 give you an equation. Okay, that's their notion of energy. But for your purposes, whatever you want to study, okay, you can come up with your own notions of topology, your own notion of energy. Okay, now, relative to that notion of energy, and is there a question? I mean, you can, somebody can stop me verbally because I don't see the chat right now, okay? You can then, relative to that notion of energy, which you can design yourself, okay, subject to certain kinds of qualities that all energy should satisfy, like the positive. Then you can have a notion relative to that of local maxima, like this top of this hill, and local minima. And I think I said this before, this idea that that if the system is at a local critical point, that means it's at the point where infinitesimally it's stable. Sorry, not stable, it doesn't move, not stable, it doesn't move. But if you were to perturb it slightly, the system, okay, then it depends on the nature of that critical point. If it's at the top of an energy peak, then no matter how you perturb it, it will roll downhill, so to speak. But again, the downhill is tricky. Okay, it should be rolling toward, the system would evolve toward lower and lower energy. That's called an unstable equilibrium. Okay. Whereas if the local energies around this particular critical point are all higher, that means it's a base, right, a basin, then no matter how you perturb the system, then it tends to settle back into this local equilibrium point, the local minimum. So it's called stable. Now, perturb, what does perturb mean? It's really up to you. Are we talking about, let's say, legislation and all the different ways that people challenge law, for example, or it could be something like, whatever, tariffs, etc., or food security. I mean, it's up to you. Now, what's really interesting about the right-hand picture here, metastable equilibrium, is where these critical points describe the energy behavior of a system that's, if you perturb it one way, it will fall apart. It will tend to continue to diverge away. The system will diverge away from this critical point toward ever lower energy values. That means it falls apart. If it were an organism, that means it would die, tend to die. But if you perturb it maybe in a different way, then it settles back to where it was before. Okay, it persists. And this is Longo and other people's basic point, is that what's really interesting about living systems, unlike physical systems, is that we seem to be always in this kind of state of metastability, and even after perturbation, we remain in a state, it may be a different state of metastability, metastable equilibrium. We persist. That's what they mean by extended criticality. It's very profound. I think it's very, very, very profound. And what I would add to that is that it's not just along a certain narrow, thin band or string of points where it's all metastable, but no, I think that we should add this notion of density, that the region of metastability is actually, actually a dense set. Okay, we can talk about that some more. Am I missing some chat? I don't see chat here. Yeah, I can keep going. Okay, sure. Go back. Okay, third point. Fourth, this you can go and read the paper yourself, but I just pulled it out of the paper. Okay, there's some interesting phenomena that happen for all sorts of dynamical systems as they near a critical point. And I'll say what this means. Okay, these terms mean. See, correlation lengths and let's take the example of a lake that becomes more and more algae laden with algae. Okay. If the lake is relatively, free flowing, there's some regions maybe near the shore where there might be some reeds growing, maybe some other region where the water is stagnant. So yes, there's some algae there. And then maybe in the middle of the lake where the water is flowing freely, the water is pretty clear, let's just say, okay. And the chemistry and the biology, the metabolism, metabolic processes in different parts of the lake are relatively local. Okay, there may be some long range effects. Maybe the quality of the water is coming down from the glaciers feeding into the lake. Yes, it does have some impact on it, but that's one impact, one kind of influence. But a large part of its chemistry and its metabolic processes is really a function of what's happening, or the quality is local, nearby. Okay. But it turns out that when the dynamical system is edging close to what's called a tipping point, right? It changes from one regime to a different kind of quality of the regime, what Simon Dong calls phase, okay, phase. Then the qualities of the behavioral system in the region are no longer just a function of what's happening nearby, but are dependent more and more and more on what's happening longer and longer distances away. Okay, so that's a general feature actually of dynamical systems of sufficient complexity as a near critical point. It's very interesting. Okay, there are others. I won't mention the other three. Okay, but okay. And then this one here has to deal with this question of complexity and order. People like Stuart Kaufman talked about order out of chaos. And unfortunately, both order and chaos are sometimes a bit confusing to depending on how you interpret it. But if by order we mean states that are have lower probability, okay, in other words, they're more rare. Okay, then a system that's a physical system would tend not to exhibit that state, be in that state very much. Okay, so entropy, right? That's what also thermodynamics would tell us that systems will evolve in toward configurations where the states corresponding to those configurations are more probable than not. Okay. Now, I know behind this is actually assuming that we have a notion of probability. So let's mark that and set it to one side. The key point for this part here from Longo and Pani is they have a much richer notion of complexity, a metabolic complexity, okay, which is not just an abstract notion of probability, but more based on the materiality of the organisms here. One, it's the differentiations of lineages, either of cells or organisms, to this point, and the degree of differentiations. Second, let's say the synchronic, let's say complexity, the diversity of the forms of structures and forms that we observe. And third, in terms of the living process, the complexity of the functional relationships obtained. Like if in the living body, different kinds of functional relationships that the organs have with one another. And the extension of thermodynamics to this kind of complexity, this kind of metabolic complexity, is basically the statement of those two equations. Okay, that the complexity is always increasing. Okay. I'll pass over this part about photosynthesis. Sorry for lack of time. And lastly, here, okay, the indeterminacy of living organisms. For this, I'm going to quote Stuart Kauffman's work. So, and he has a nice cartoon. I'll skip over the formal definition. Here's the story from Stu Kaufman. So, and this is a parable, okay, that he tells. Let's just say after, I don't know, several hundred million years, we already have now in the ocean sufficiently complex soup to sustain these unicellular organisms, okay? And these particular creatures, Patrick, Rupert, Sly, Gus. And they're floating around freely in this water, in the lagoon, 1 billion years ago. And they're free floating, and they absorb nutrients from the ambient water, and they excrete and do whatever they need to do. But let's say by accident, one of them gets attached to the rock, stuck. And it turns out that it can think better because it doesn't have to waste so much energy, expend so much energy going through the free water. By the way the currents are flowing, it actually gets a whole bunch of nutrients flowing by the rock. So it becomes the first sessile feeder. And then let's just say after a while, a whole bunch of them start to take advantage of this accident, okay, this accidental affordance, this adjacent possible. And then some other creatures come over, and by accident, they gobble up one of these creatures. It's the world's first predator, unicellular predator, okay? So that the Patricks become an affordance for the Ruperts. They become an affordance for these what turns Ruperts into predators, okay, and Patricks into prey. But the whole point here is that those functions did not predate the occurrence. Okay, that's the crucial point. That is, niches and species co-emerge. Okay, that's what Stuart calls adjacent possibles. Okay, that these novel life forms, by coming into existence, they constitute contexts that afford enabling constraints, right? That afford opportunities. So that's why they're called that's why he calls them adjacent possibles. There's not cause, they enable. Okay. And there's both Stephen Jay Gould and Stuart Kauffman, and then mathematically, Longo and Montague have modeled this kind of development as a diffusion process, which is a bounded diffusion process, which steadily increases the span of complexity. There's no a priori kind of tails, of course, to the kind of structures that are evolved, right? And they evolve in ever more, they proliferate into ever more greater complexity. Okay. And the key thing here is that there's no way, this is the argument that these people are making, is that there's no way to ahead of time write down a law or an equation or even a space of all possible futures, possible future configurations or states for a biological system. Okay, so these are unprestatable. Okay. So there are no, what Stu would call, no entailing laws for life. Okay. So this has nothing to do with computability. It's a much deeper claim. There's no entailing law at all, computable or not. So let me pause here. So this is just, and this is just an overview, but I invite you to look at this yourself, the article yourself. I think some of you have already taken this up. Okay. So let's see what I have. Yeah, okay. Let me just pop in on. I'll end on this one frame, which I'll share with you now, and then we can have a discussion. We got some time there. So share. Okay. Yeah. I'm skipping over a lot of argument here, but I want to summarize the arguments that have been made by these people from theoretical biology that we're drawing from. Okay. That basically, one way to put this is that physics, the way Joseph Longo puts it, conditions but does not determine biology. So, so maybe that's a spirit in which we can take all of these kinds of accounts, whether it's topology or logic or physics, is that we can think of these as some of them as conditioning, what we can say, but they don't determine what we can say, okay, or do. All right, and that's a key thing. But just to remind people, there are very, very strong limits, like the Gödel incompleteness theorems and Turing undecidability theorems, on what algorithms can, the span of expression of and of what algorithms can account for. These are very strong. And they're even stronger than computability, even so that what mathematicians can invent and prove is actually greater than the span of what can be determined in a formal way, by a formal system of inference based on axioms. Okay, so that includes, in fact, computation underneath that, but I don't have time to go through that today. Okay. I just want to say that we have a lot of freedom in terms of what we can conjecture and what we can prove. Okay, let's open it up if we have time. 3 minutes.
If anybody has any questions or comments, just feel free to open the mic and speak.
Yeah.
I had a question more generally about the status of topology. Can you hear me actually?
Yes, yes.
Okay? Ah,
Yes.
Okay. So I don't know if how familiar you are with Kant and how much it plays a role in what you research on. I've been trying to read the Critique of Pure Reason recently, and there is this whole chapter about schematism and this problem between, let's say, mathematical or like categories on one side and space and time on the other, and how to bridge them. And somehow I see in topology something a bit related to this, right? That is like how to use very, very, how can I say it, strictly, because no word really works there, but let's say static mathematics in time and space, let's say. And I wanted to know if this makes any sort of sense, and if there is maybe some literature I could read about this, and also because schemata are something different than models, and also this would be interesting to talk about, because you said, yeah, models are, or what we understand as models is a very small part of what topology is actually dealing with, and yeah, I would be interested in your thoughts.
Yeah, that's a very deep question. I mean, I'm thinking that that's why I meant earlier maybe about, well, this could be related, I think, to what I said earlier at the beginning about trying to think about the living process of doing topological thinking or mathematical thinking in general versus using mathematics as instrumentally. So yes, if we would use mathematics instrumentally to provide certain structures to give a description of X, whatever X is, yes, then one could say that's a schema, maybe, or model or something. Okay, but certainly that's different from the process of, you see what I'm saying, of, let's say, topologizing or thinking about, bounding processes by other processes, or the actual living practice of doing mathematics or creating mathematics on the fly. So that's it's not me. I mean, I think there's a lot of, there's some people who are trying to think this through. And well, yes, I include myself in that group of people. There's going to be a conference in November 9 and 10 in Paris in Economal called, I think the historicity of life, the open historicity of life. I'll send the link out to that. That's one project trying to think about kind of a genealogical historical way, but also including mathematical accounts for that. And even more profoundly, this work by Jean Petitot and Bitbo, and maybe Cecile knows you people already, who some years ago tried to historicize objectivity, like concept itself. And I will look for the references for that, because I don't understand that quite enough to talk about it yet. And I'm not sure if that escapes a formalism. I don't know. Okay. Whereas if this recent work from Alessandro Sarti and Giovanna Citti on differential heterogenesis, all that kind of work, they were explicitly trying to draw from Deleuze and from process philosophy. Okay. That's motivated them to try to come up with a mathematics that is actually adequate to that kind of processuality. Okay, and this may be one way to step around the problem of schematization. Okay, but I'm not sure. Okay, we don't know, but at least some of these people are aware of that. That's the problem. Yes, Alexandra.
Yeah, just to clarify, am I right? Like if I want to describe a particular point or unit inside of set, like for example, in geometry, I will use coordinates to describe the particular one. But in topology, will I use some kind of features to describe it, or relations to another points inside of this set? Am I right?
Yes, in the sense that we don't have both power and we don't have coordinates in topology. We do have indices. You notice right now, the infinite sequence, the first, second, third. So there's such a thing as index for certain purposes. But even in that case, the power of some kinds of topology is that there are always, not always, sorry, there are moves to say, can we go from, let's say, what's called like sequential notion to a notion that depends on the topology, but not on sequence. And this move back and forth is part of what people do at the beginning of this field, in fact. So it's these different ways to detach from metric notions happen also at this level of indexing, let's say, the sets. I haven't gone to that very much here, but the most profound way to do that might be through what's called category theory. And in a sense, category theory might be kind of relativization to get around this question of model and schema, which I think I'd like to understand more with you, Raphael, okay, another time. But category theory is the most sophisticated way so far to relativize questions of schema and truth. But that's a whole other course. I think there was a course in the new center about that at one point. Okay, next week we're going to jump to the questions of process individuation. there's no way to cover really adequately any of this. I mean, Cecile is far more capable, qualified to do that about simulation than I am. But what I would like to do is to bring in some of the mathematical notions that may help one either get a grasp of some of the notions, not just mathematical, but also physics ideas, to get a grasp of where maybe Simon was drawing some intuition for some of his work. And also, hopefully, to allow us to work with him to extend, to develop applications to some of his notions. And next week is when I like to talk about the work that I mentioned earlier on differential heterogenesis. This is very recent work by Alessandro Sarti and Giovanna Citti. And hopefully that'll be another way to think about the kind of processualist approach to living matter. Okay. So, thank you. See you next Sunday. And I'll be in Central European time.
Thank you so much, Xin Wei. I hope you get some much deserved rest now. This is quite a massive privilege to have such a master class from you and to make it so intuitive for the non-mathematicians among us.
It's unbelievable that the amount of ground we covered is just unbelievable. Like we went from math to metabolism. It was just fascinating. Thank you very much.
Very few equations and very few numbers. You see?
Yeah.
That's great. All right. Take care.
Okay.
Bye-bye.
Thank you
Thanks,
so
everybody.
much, Xin Wei.
Bye,
Thank you
bye.
so much.
Bye.
Bye.
Bye.